good. Okay. Thank you. So let's have our last section of the carbohydrates. We'll talk about polysaccharides, and then we will talk about more detail of the starch. So first of all, polysaccharides. Now we already talked about the monosaccharides. So monosaccharides, we talk about the example is glucose, and then we talk about oligosaccharides like lactose, sucrose, and maltose. We already talked. So we move this one to polysaccharides. Polysaccharides, first of all, we think about the carbon unit is more than 10. Sorry, not the carbon unit. It's composed by the glycosidic amount of the monosaccharide is more than 10 monosaccharides composed by a large sugar, a large polymer. Actually, in our life, 90% of them, the carbohydrate resource, is coming from polysaccharides. And a good example is starch and cellulose. We will talk about this starch in much more detail very quickly. In order to evaluate or we quantify or we say characteristics of the polysaccharides, we introduce a terminology called DP. And we will mention this again later on. This is called degree of polymerization, which means how diverse it is. Which means how many numbers of the monosaccharides. Right here you can see most of them are 200 to 300 degree of polysaccharide, of polymerization. But for starch and cellulose could be more than. This is somewhere around 5,000. And this could be around 10,000 or even more than that, to like 15,000. So it is huge and a large molecule. Now, based on the diversity, because most of the starch coming from is glucose, composed by glucose. So we call it a homoglycan. However, there is some other products which is composed by the different type of the polymers. Therefore, we have heteropolymers. And the heteropolymers could be di and also could be tri. It depends 2 or 3 heteropolymers. So these are just as opening remarks when we talk about the polysaccharides. Then we want to talk the whole class more detail about the starch. And we know starch all the time. We eat like a bread, pasta, noodle, all of them are composed by starch. So, and the beans even. So what is starch? First of all, this is a major plant storage carbohydrates. And a uniform molecular formation is C6H10O5 multiplied by N. That's a uniform formula. what is the starch looks like, the characteristics? It is white color, everybody knows. It is odorless. And do not have a taste if you do not add anything there, so it's tasteless. It's undissolved in cold water and in alcohol. Well, of course, if you heat it, it will be swirling. We will mention this gentilization real quick, and then become maybe a gel formation. Okay? Number 4 we want to mention here is we can see the structure of the starch using light microscope. Using X-ray diffraction. Remember, we find the structure of the DNA double helix use X-ray diffraction back in 1953. We also can using our textbook showing is laser confocal microscope. This laser confocal microscope could show you 3D images, which is connected to the computer and using argon laser as an energy resource and connected to the computer system. Of course, you have to do a basic scan. Then some of the light wavelengths will be absorbed and some of them will be refracted. Then we'll see very clear 3D images. So this picture here in our textbook is actually new, not in a 3rd edition, which is showing you the 3D images of starch granule using confocal scanning laser microscope, which is laser confocal scanning microscope. It's the same thing. You see the first one is potato, second one is corn, then tapioca, wheat, mung beans, and sweet potato. It's a major resource for starch in the United States and also in the world. About like 80 to 90% is coming from those. Okay, so you can see very clearly talk about the particles of those large starch. Okay, now then we will be spending some time to talk more detail about the starch granule when they're composed by millions of Mylopectin and with Aminos. So we want to spend some more time to talk about this. Okay, so starch is composed by 2 major parts. Number 1 is called Aminos. So Aminos composed about 20 to 25%. Average. Some of them are small. Let's say corn and rice are small, 70%. Pea and the cornstarch could be up to 75%. So it's a huge amount of the Aminos. Okay, Aminos composed by alpha D glucose. It is a structure, is linear, helix, and composed by 1 to 4 glycosidic bonds. So what it looks like? It kind of looks like that. Okay? Now, this is the linear. every these twists or these helix, if you want to see more detail, it is composed by 6 alpha D glucose. Okay, now then there is a question. What does this mean by 1,4 glycosidic compounds? This is we're going to go back to the original talk about the structure. So this is a glucose. Okay, then so that's another one. This is carbon number 1, carbon number 2, number 3, number 4, number 5, and number 6. Goes here, carbon number 1, number 2, 3, and 4. They are combined by this longer and longer like a polymer. Could be 400 units. Could be 2,000 units, it depends. Okay, that's become a amylose. That means when the carbon 1 and carbon 2 combined by oxygen, that is called 1,4 glycosidic compounds. Now each twist, each helix is combined with 6 alpha D glucose. Now, usually, most of the time, these amylose are actually connected together. They connected together with hydrogen bonds. Because of the connected together with hydrogen bonds, so they kind of hydrophobic. Originally, it's actually not really absorbed water at all, so they don't like water. That's why it's not dissolved in the cold water, because of this hydrogen bonds. Okay? So this is a picture here for amylose. Now do you want to help me a little bit there? Now we want to talk about here, in the second component is Mylopectin. Okay, this guy composed by 70 to 75% inner starch products. This is actually a large molecule. This is a low, large molecular stuff. That is a low molecular stuff. Now, amylopectin, what it looks like, it is a branch with 1 to 6 glycosidic bonds. So what it looks like, lots of them will say like a tree, or some of them like that. If you want to see more specific, our textbook has one thing. It kind of like a light to put in your dining room. Then, if you're more specific, you may see something like this, something like that. This is Mylopectin. Okay, we call this is like a band. or A section. And we see these are B bands or B section. And A bands, which is outer, unbranched. The B bands most of the time is inner and branched section. And then you have this long tail. This is called a C band or C section. This here has a reducing end. Okay, this is the basic structure. So it's a large molecule. Then what does this mean? 1 to 6 glycosidic bonds. This you're gonna go here to see. We're gonna talk about it again. Okay, so we draw it right here. Then this comes. What's going to happen right here? I said this is number 1, number 2, number 3, 4, 5, 6. So what that means? It's going to connect it to this guy. This is carbon number 6. So what this means? That means you have to draw is kind of like this. Okay, so you see OH, H, OH, H, then go H, OH, and then go H, OH. There have to be a little bit angle there. And this is number 1, this is number 6. And this bond is to called 1 to 6 glycosidic bonds. Okay, that is what they really means. Keep in mind. Okay, so this is a small molecule. Smaller, and that one is larger. Now, most of the time, we mentioned averagely, the amylose in a starch is about 20 to 25%. P and cornstarch 75%. Now, amylopectin is higher. We also can manufacture or chemical synthesize some of the starch, which is called a waxy starch, or called waxy corn. The waxy starch, or we say waxy corn, this will make it almost to 99 to 100% amylopectin, and not amylose at all. That's possible. Okay? So that's something we want to give you an introduction. Now, of course, the components of amylose and amylopectin, the ratio is very important. It depends on different plant resource. And we will talk about it later on. When we move to talk about generalization and ritual gradation, we will talk about that part. Okay, next one, this slide, we talk about one of the obvious phenomena. I'm not sure about you still remember in the class, which is general microbiology. Some of you didn't take, some of you took it. If you still remember, how we test Aminos. Bacteria has Aminos. We use a starch agar. We just buy a starch, put it in the agar. Then we split the agar plates onto 2 sides. One side we inoculate Bacillus cereus. The other side we inoculate E. coli. And we know the Bacillus cereus will generate amylase. Now, actually, it's not really amylase. It's one of the amylase we will be mentioned real quick. It's called prurinase. not really aminos. It's just belonging to the group of aminos. Then I say, how we got the test? How do we know the bacteria use the starch there has aminos? Remember, the method is we got to pour iodine solution, and then we mix it. If the iodine turns brownish color, that means the starch has not been used, and the bacteria do not have aminos. So end up with here, ideally should be no color, and on the other side with E. coli, this should be turned brownish color because E. coli do not have aminos, and this agar should be showing the reaction between starch and the iodine. Now why they can do like that? Because they have this twist, have this helix, and they could be combined with iodine solution there, one molecule of the iodine. And the color of the reaction between starch and iodine, it really depended on the chain length. So for example, at this moment, when we see the starch agar is showing brownish color, this chain is approximately 12 to 14 units. And also with 2 helix twisted, possible. Okay? So the chain length is important. With the increasing of the chain length, it's going to turn from brownish color to red color. If you reach 30 to 40, then it will become red. And this is a very easy test, but I tell you one thing, in the industry, they're using starch iodine method to measure the amount of the starch for a long history. However, this method, they do have a disadvantage. We know the total amount of the starch, but we cannot differentiate dissolved and undissolved starch. So therefore, what's going to happen? We're using another one called the microwave assisted method. With this method, we can differentiate dissolved and undissolved starch. Okay, so you can see here, the color produced by reaction of iodine with amylose, different chain lengths. 12 usually with 2 helix terms is brown color. When you see red, purple, blue is the increasing of the chain lengths. Red is about 30, purple 35 to 40, blue is about 45, and much more helix terms. Okay, its understanding is like the color is mixed together. Now, we also want to briefly mention starch is like a powder, but also it's partially crystalline, about 15 to 45%. And basically, there is 2 different types of the units, or type of the morphology. The A polymorphous and B. Now, A usually it's loosely attached. So the crystalline is not very strong, so it's not easy to absorb the water. So few A type will be allowed only few structured water molecules. When the B comes, it is more welcome to water because it's more unattached and more loose in the space could attach more water. Now when you attach more water, what is going to happen? It's going to be showing you appeal the light under microscope. So they have a terminology to describe that. That is called direfringence. F-R-I or F-R-I-G. Because this is like a pure light with cross-linking fiber. Okay? Now, what is crystallinity? This is intertweeting the amylopectin with a linear component of usually over 10 glucose units to form the double helix. Okay, so I'll let you know a little bit. There's a little bit of crystalline there, about 15 to 45%. This is the one we already mentioned. The picture A, which is showing you, is a typical molecule of amylopectin. We see the A chain or A bands, B chain, we mentioned about C chain with the reducing ends. The B picture, which is type B, have amorphous and crystalline region. This is typically showing in a banana products. You will see the amorphous region and the very crystalline here. Now the picture C is showing you, it is a good combination of amylopectin and amylose. See all these amylose and these amylopectin. Okay? And this looks like a bean, like a pea, all these products. And this B picture will show you a twisted, and you can see one twist, one helix is about 6 glucose units. So this gives you a picture of the starch, and typically is amylopectin, what it looks like, and the combination with amylose in a banana, pea, and the bean products, what it looks like. Now we want to talk more detail is major characteristics of the starch. It's called gelatinization and retrogradation. So we want to spend more time talking about this. Okay, so we talk about the starch, gelatinization, and which is coupled by the concept called retrogradation. And some people say it's retrodegradation. It's the same thing. Okay. Okay. So I'm going to give you some of the example. Gelatinization. You want to talk this slow and more clear. I'll give you an example. When we talk about the starch gelatinization, we actually talk about is starch reacted with heat. However, before we talk about this gelatinization, we want to talk about another thing.